So now we're going to kind of tie together some of the concepts from lesson one with this idea of successful collisions. So we're going to look at the factors that will affect reaction rates. Now, all factors work either by changing how often particles collide, so this idea of collision theory, or changes how many particles have sufficient energy for a successful collision. So the first factor that we're going to look at is temperature. Now, temperature is an easy one. If they ever ask you, how do you increase reaction rate? Your answer is increase the temperature. Why? Because when you increase the temperature, you increase the average kinetic energy of the molecules. So think about when you raise the temperature of something, molecules move faster. They contain more kinetic energy. So if you look at this diagram, this distribution table here, we've got this one curve at 0 degrees Celsius, where it's a pretty nice little bell curve. And if we have the threshold energy being this line here, you have very few molecules that have sufficient energy for a successful collision. If you raise this temperature to 25 degrees Celsius, you've got this line coming in here. You have more molecules that have sufficient energy for successful collision. But if you can raise that temperature to 100 degrees Celsius, you've got this last curve coming out here. You would have the most molecules with sufficient energy for a successful collision. So what does increasing temperature does? Increasing temperature increases the kinetic energy in the system. It excites the molecules, which means more molecules will have sufficient energy for a successful collision, and therefore the reaction rate will increase. Awesome. So that is changing how many particles have sufficient energy for a successful collision. But temperature not only does that, but it also affects collision theory. Because the molecules are going to be moving faster because you've increased the kinetic energy of the system, the molecules will collide more frequently and the reaction rate will also increase. So again, to have a successful collision, the molecules have to hit and they have to hit with enough energy to react. So if you can increase the energy they have and increase the number of collisions they have, you're really going to increase the temperature or increase the reaction rate. There's another thing that's going to become important for some of your Hebden questions that you do. When you have a slow reaction that has a high activation energy, so something kind of like this first bell curve, so the 0 degrees Celsius, right? It would be pretty slow because there's very few molecules that have sufficient energy for successful collision. If you can increase the temperature by 10 degrees, it will approximately double the reaction rate. So there's some questions in your homework that I didn't put in here, but it'll say something along the lines of a temperature at 10 degrees Celsius has a reaction rate of blank. If you were to increase the temperature to 30 degrees Celsius, what would be the reaction rate? So if you went from 10 degrees Celsius to 30 degrees Celsius, you have two 10-degree um, temperature increases. So there's two 10-degree temperature changes, which means your reaction would go 4 times as fast. So you could take whatever reaction rate they give you and just multiply it by 4. So just be aware of that. It's a really good thing to know. But I will also emphasize, this only works for slow reactions with a high activation energy. If a reaction is already fast, and you increase the temperature, it is not going to double the reaction rate. So there'll be some wording in there that mentions having a slow reaction with a high activation energy. Okay. The second method for increasing your reaction rate is going to be mainly to do with collision theory, which is that if you can put more particles in the same volume, they're going to hit more frequently. So if you started with a low concentration of reactants and you were able to increase the concentration of your reactants, they're going to collide more frequently and the reaction rate will increase. So molecules will collide more frequently and the reaction rate will increase. So again, there's two ways of increasing reaction rate. Number one, giving more energy. Number two, hitting more often. Okay? Those are your two sentences. Now there is a really important statement here is that this only works with gases and aqueous solutions. If it is a solid, throwing in more solid is not necessarily going to increase the rate of reaction. There's other things that we can do with solids. But when we're talking about gas and aqueous solution concentrations, then you can increase the concentration to increase the reaction rate. Because you can tell there's going to be some questions that are going to say, how could you increase the rate of reaction? Right? And they're not all going to be true. The next one is increasing pressure or decreasing volume. This is going to be only with gases. So increasing the concentration works for aqueous solutions and gases. This one is only gases. So what's going to happen is you're going to take a canister, so something like this one here, and you are going to decrease the volume. So all of these particles have all this space to cruise around in this first container. Whereas in the second container, there's the same amount of particles, but they've been compressed into a tinier space. What's going to happen? Well, that's going to increase the pressure within the system. When you decrease volume, you always increase pressure. What does pressure mean? Right? How do you monitor pressure? I can't talk and write. I'm going to start that again. Increase. There we go. Okay, what does that mean, increased pressure? Well, pressure is, when I think of it, is the number of times that your particles hit the edge of your container over time, right? So if you think about this first one, like these molecules are going bing, 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 right? There wouldn't be a lot of pressure. Whereas if you think in here, it's like bing, 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 it would be constantly hitting the side of the container. So that's the increase in pressure. So it's putting more pressure on the container. It wants it to expand. What's really going to happen here is that when you condense the space, you're increasing the pressure, but it's kind of like increasing the concentration of a reactant. There's more in a smaller space, which means that the molecules are going to what? Is there going to be more energy in the system, meaning there's more energy for successful collision, or would they collide more frequently? Well, they're going to collide more frequently. So molecules will collide more frequently, and the rate of reaction will increase. Okay, so we're going to do a little mini break here. So we're going to ask two questions before we go on and talk about the last few ways of increasing reaction rate. I'm going to give you two reactions, and we're going to look at which are, out of these three methods, which of them could be used to raise the rate of reaction in these. So first one, temperature. If you increase the temperature, I'm going to type that, write that. Number one would be increased temperature. Increasing temperature always increases the rate of reaction because you're increasing the average energy of the system. So more molecules have sufficient energy for a successful collision, and they're going to collide more frequently. So more energy and more collisions. Secondly, can we increase the concentration? Can you increase the concentration of gases? Yes. You could increase the concentration of hydrogen gas, or you could increase the concentration of iodine gas. Okay, either one of those. So increasing the concentration, you would get more collisions. And there's just more molecules, right? So there would be more molecules that would have sufficient energy for successful collision. And number three is you could decrease the volume to increase the pressure of your system. And again, you would have more collisions. Awesome. All right, try this next one. So this next one, maybe not all of them would work. Of the three this time, so the other one we were naming the three ways, but now of the three ways, which of the methods could you use to increase the rate of this reaction? Hopefully you're all thinking increased temperature, right? Increased temperature increases the energy and increases the collisions, right? They're just moving more. Could you increase the concentration? Well, these are both solids, so nope. Could you increase the pressure of your system? Is this a gas? Nope. Right? So the only way we could increase the rate of this reaction would be increasing the temperature. Awesome. Let's go on to the last couple. The next thing is just the ability of reactants to meet. So this is talking about collisions. You need collisions to happen, but you need the reactants to actually meet each other. So if you think about this last reaction we did, we had copper and sulfur as solids trying to react to become copper sulfide. Would that really happen? Like if you had two blocks of solids sitting near each other, I mean, are they really going to react? No, you'd have to actually probably increase the temperature to get them to even do anything because the particles are kind of trapped in a solid. They're moving, but they're trapped. So the first thing we're going to look at is phase considerations. This affects the ability of reactants to physically interact. So like a solid chunk of two solids, unless they're like touching, there's not going to be a reaction that happens. And how much they're free to move around and touch other molecules. So we always say solids, they're the slowest, right? Their particles can barely move, and they definitely can't freely move. Liquids and gases are definitely faster. The gas particles are like they're just fast and they're whizzing around, but unless you contain them, they're kind of all over the place. Liquid particles are better, they're close in proximity, but what's the best is aqueous solutions. Aqueous solutions, it's kind of like having a liquid, but it's not a pure liquid, it's a liquid with dissolved ions. So the ions would be in close proximity in the solution. They can move around in the solvent. And there's also this positive negative charge attraction, right? So you could have a positive cation attracting a negative anion, and they're going to want to collide, right? So there's lots of things with aqueous solutions that make them want to react. So the overall speed ranking is aqueous over gases or liquids over solids. So if I asked you which of the following reactions would be slowest at 25 degrees Celsius, what would you think? Well, it's going to be the one with all the solids, right? If I asked you which one would be the fastest, which would it be? Aqueous. Right? So this would be hydrogen ions and hydroxide ions floating around in solution. Of course, they want to make water. So that would be your fastest reaction. After that, I would probably go for the gases, right? And then my second last would be the magnesium with the hydrochloric acid, and then down to the copper solid and the sulfur solid. And again, with these gases, there'd be some parameters, like you'd actually have to contain them so that they actually do collide, right? Because gases are a bit of tricky. They're fast, but they like to escape. All right, the next one is surface area. So surface area is something that affects heterogeneous reactions only, meaning reactants in different phases, so like solids and aqueous, or solids and liquids, or gases and liquids, or anything kind of along those lines. The key thing for me is that I only really think about increasing surface area when I'm talking about solids, right? Because what happens is that reactions occur when things are in different phases only when they're able to meet. So only on the surface level. So if you had this solid that was a giant chunk, right? So let's say this is a giant chunk of, I don't know, I'm trying to think of a giant chunk of what? Copper. We've talked a lot about copper today. So this is a giant chunk of copper. And then all of these ions are trying to react, but they can only react with the surface that's available. There's all this copper inside that isn't available to react. So if we can increase the surface area of the solid by things like grinding or crushing or slicing or something along those lines, we would increase the surface available to react. And so all of a sudden these ions are getting between the cracks and they're able to react at all these little surfaces. So increasing the surface area exposes more particles to react at the surface, and molecules will, here's our famous sentence, collide more frequently, and the rate of reaction will increase. So just a quick little question. Which of the following changes would increase the rate of reaction? So I've got calcium carbonate with hydrochloric acid producing calcium chloride, carbon dioxide, and water. Would using a larger chunk, so would adding more mass of calcium carbonate work better, right? Instead of a powder. So should I use a huge chunk instead of powder? No, obviously not. Because if you think about the large chunk, then I'm only having reactions happen at the surface. What about crushing the calcium carbonate into a fine powder? Well, if I crush it into a fine powder, all of a sudden those reactions can happen at all these little surfaces. So that one's definitely a possibility. What about decreasing the concentration of hydrochloric acid? Well, that's decreasing the concentration of a reactant, so definitely no. What about cooling? Definitely no. We always want to increase the temperature. We want to increase the average kinetic energy of the system. So my only answer would be B, increasing the surface area of my solid. All right, last three. The next one is called a catalyst. We're going to be talking about catalysts more later. But catalysts are just something that can speed up a reaction, right? They speed up a reaction without being consumed. And the way that they do it is they provide an alternative pathway with a lower activation energy. So you'd have a reaction happening, and that reaction could happen, but a few of the molecules could go a different direction and take this path that requires less energy. And so you would have what? You would have more molecules will have sufficient energy for a successful collision, and the reaction rate will increase. So catalysts are something that we can use to increase the rate of reaction. And again, we're going to talk more about that, but all you have to know is that they lower the activation energy so that more molecules will have sufficient energy for a successful collision. The next one is not how to speed up a reaction, but it's actually how to slow down a reaction, which is an inhibitor. So an inhibitor is something that decreases or stops a reaction. Now, why would you want this? Well, because sometimes there's like a poison and you would want to stop it, right? Or antibiotics can stop a virus from attacking, or antidepressants can block your serotonin or block, what do they do? I don't know if they open more receptors or if they block certain ones. Anyway, sunscreens, right? A physical block. We don't want to have that reaction on our skin. Preservatives, we don't want our food to be rotting, so we want to preserve it, which would decrease the reaction, the oxidation reactions. How do they do it? Well, there's two ways. They can block a reactant, so they can stop something from being able to get to the reaction, or they can deactivate catalysts, right? That's all you need to know. And then the last one is kind of simply just something that's out of your control, which is some reactions are fast and some are slow naturally. So some reactions are naturally slow because their bonds are very strong. There's unreactive reactants. Electrons are tightly held, right? Electrons have a lot to do with whether a reaction happens or not. This is often covalent reactions, so anything requiring a covalent bond, so two oxygens, or sorry, two nonmetals. So for example, here you have an oxygen bonded to an oxygen, and that would be a really hard bond to break. So this reaction of carbon solid breaking up or combining with this oxygen molecule is not going to happen very easily. Whereas some reactions are naturally fast because they have super weak bonds or the electrons are loosely held. This is mainly ionic reactions, so metals and nonmetals, especially in solution. So things like if you had a silver ion and a chloride ion floating around in solution, it's pretty easy to plunk them together and precipitate out a silver chloride. Now, there won't be a lot of questions about this because you're not entirely expected to understand the nature of reactants, but it will be made into a fairly obvious question where you'll look at it and be like, oh, well, something like this would happen very fast versus something like this, where bonds have to be formed or broken or they're covalent or something along those lines. So before we finish up this unit or this little section, let's just do these, what is there, 3 questions of something that you might see in your homework. So first one, consider this reaction of zinc and hydrochloric acid producing zinc chloride and hydrogen gas. Which of the following would increase the reaction rate? So we've got increasing pressure, increasing temperature, increasing the concentration of hydrogen gas, and increasing the concentration of zinc chloride. Which ones do you think? Well, let's start at the end and work our way back. Increasing the concentration of zinc chloride. This is the zinc chloride. It's a product, so no. Increasing the concentration of hydrogen gas. That is a product, so no. So now we're down to this is a multiple choice question, and we have to choose either increasing pressure or increasing temperature. Now, when you first look at this one, you're like, oh, increasing pressure. Look, there's a gas. But the gas is not a reactant. So for both of these were products. Increasing the concentration of a product does not increase the rate of reaction. Increasing the pressure, there is no gas reactant. So even though a gas is produced, there's no gas reactant. So increasing the pressure of a solid and an aqueous solution, those have defined spaces. You actually can't compress the molecules into a smaller space. So really the only answer is increasing the temperature. Okay, what about this next one? Which of the following reactions is most likely to proceed at the greatest rate under standard conditions, meaning not an elevated temperature, not an increased pressure? So we sometimes call this standard temperature and pressure. So the temperature would be like 25 degrees Celsius, and the pressure would be, oh geez, I shouldn't have started that. What is it, like 101.3 or something like that kilopascals, whatever it is. Okay, so if you look at these, which one's going to be the fastest? Well, definitely not the two solids. Okay, and then what are we down to? We have two gases. We have a solid and a gas. We have these aqueous solutions. The aqueous solutions are always going to be the fastest. So this one was about phase considerations. Okay, this next question I quite love. So you're investigating a reaction and you found the following data. And we want to determine which of the following factors explains why the rate in experiment 1 is different than the rate in experiment 2. So this experiment was equal moles of zinc and equal volumes of hydrochloric acid were reacted. After 2 minutes, the volume of hydrogen produced was recorded. So in here we have zinc, right, was one of my reactants. It was either strips or powdered. Which of these two do you expect to be faster? Well, powder should react faster than strips. And then when we look at the temperature, 10 degrees Celsius versus 15 degrees Celsius. Well, this should be faster. Then we look at hydrochloric acid concentration. So again, the concentration of one of my reactants, it is greater here, so this should be the faster reaction. And then what we're going to try to do is explain the rate of hydrogen produced, really, right? So this is my measure of my rate of reaction. Why? Because it's how much product is produced. So here, this is way more, which means that experiment 1 must have been faster. Well, according to the state, or that's not state, sorry, the surface area, powdered should have been faster, but it wasn't. According to temperature, the 15 degrees Celsius should have been faster, but it wasn't. So the one thing that must have made this reaction faster must have been the concentration of hydrochloric acid. So the hydrochloric acid is the only thing that was working for experiment 1. It was the only thing increasing the rate of reaction of experiment 1. So temperature, nature of reactants, and surface area of zinc did not factor in because those things actually should have made experiment 2 faster. Well, not nature of reactants. That's the same for both. Awesome. All right, go and practice the questions for 1.6. That was a long one.